So imagine that you are diagnosed with cancer and a super powerful AI comes out with a conclusion that you cannot get the most efficient medicine. And an answer that will not fly, or at least that I don't think we should accept, is computer says so.
Casper Wilstrup is trying to solve AI's black box problem by using different methods than the ones we usually hear about.
There's plenty of situations where the explanation is as important as the prediction. I went rather extreme with the life or death decision about a medicine, but it also applies to situations like credit scoring, credit risk scoring, or being allowed to buy a house.
He's working on something called Symbolic AI that communicates how decisions are made and why.
It introduces a middle step where the AI generates an explanation, and then we use that explanation to create a prediction. Whereas the black box artificial intelligence approaches goes directly for the prediction and bypasses this entire idea of understanding the underlying process.
I'm Jennifer Strong, and this is Shift.
Now here on the steering column is a device called Auto Cruise. You simply set the speed you want.
Self-driving robo-taxis are already on the road in 2 U.S. cities.
As the disc rotates, a mirror reflects the light in the way that depends on how the signal was recorded.
This is the 100 terabyte Abzu. I present to you Electro, the Moto Man. Ladies and gentlemen.
I would say that one of my greatest skills is my ability to interact with humans.
This episode, we bring you the latest installment of our new oral history project. Throughout this series, we'll be featuring the stories of breakthroughs and other key moments in emerging tech, as told by those who witnessed them.
Because you're listening to this podcast, I'm assuming you're interested in staying on top of the latest trends, news, and more. So I want to tell you about another show. It's called Web3 with A16Z Crypto, but it's really about the future of the internet, future of creators, future of business, future of the way we work and live. It's for anyone seeking to understand the latest tech trends direct from experts with high insights per minute, given your time and attention are so valuable. Follow Web3 with A16Z in your podcast app now.
This was a place where I spent some of the best years of my youth, down in the basement mainly, because that's where all the cool machinery was. We used to do experimental physics actually. Didn't require as expensive equipment as it does today. So this was in the early 90s. Back then, students were the people who could code at the institute here. Like the professors, they knew nothing of coding. And then I was part of this new generation. I was born in 1971, and I started coding when I was 11 on my Sinclair ZX Spectrum, which was like a super popular little toy machine. So my name is Casper Wilstrup. I am the founder and the CEO of a Danish-Spanish AI research company called Abzu that is mainly focused on symbolic artificial intelligence, which is a subfield of AI where we try to come up with clear and understandable explanations of phenomena that the AI is thinking about, which sets it apart from what is classed as the opposite, the sub-symbolic artificial intelligence approaches, of which neural networks are by far the most well-known. We're sitting at the main entrance of the Niels Bohr Institute in northern Copenhagen, the place that Niels Bohr founded in 1920, the so-called Copenhagen School of Quantum Physics. And this has been the center of particle and nuclear physics in Copenhagen. I actually never graduated because I did my first startup company in 1999, based on an idea that we got when we were building high-performance computers right in there behind those walls. Me and a friend of mine, we built this device that allowed easier construction of high-performance computer systems, and that then became a company, and that shaped the rest of my career. So I am an entrepreneur, been involved in a lot of different startup companies, but always with hard analytical data analysis things at its center. So the harder, the more compute requiring problems are, the more I enjoy them. Symbolic artificial intelligence is a very obvious match for anything scientific. Scientists ask questions about why. They don't only want to predict what happens in a given situation. They want to understand the process that governs what happens. So symbolic artificial intelligence, it essentially delivers answers along with the theory for how to arrive at that answer. So if you feed it, let's say, Tycho Brahe's data about the orbit of Mars in, Kepler's laws of planetary motion is what comes out. And Abzu has been an R&D company that has focused a lot on inventing new approaches, reinventing, you could say, the principles in symbolic AI, and bringing that to particular science. We've worked a lot in disease understanding and in drug development with pharma companies over the years. Now we've fused our symbolic artificial intelligence together with subsymbolic methods, the neural networks, to create what we call a hybrid AI that is able to get the best out of both. So an example is we work with NASA Gene Lab. There's a lot of speculation about why astronauts get rashes. It could be the less than adequate soaping, water being so scarce in space that you really don't wash enough, and that could be a reason. It could also be something with the environment. It could be radiation, and at least what we can see, there is certainly a big genetic component. We know that the skin and the organisms of astronauts actually change quite rapidly and in detrimental ways when they're in space, but it's a little hard to study through a scientifically rigorous approach. So humans are still sending animals into space to do these things, and one of those animals are mice, and together with NASA Gene Lab to study how and what governs the changes to the cells, particularly the skin cells of the mice, because those are the ones that change the fastest. But the bigger picture here is to try to understand the genetic makeup of organisms that are most impacted by the environment that you meet on, in this case, the International Space Station. So in science, we're looking for the simplest possible theory that will fit the data. So having two theories, one complex, one simple, we prefer the simple over the complex one if they have the same predictive accuracy. That's the scientific method or principle that we call Occam's razor. Subsymbolic artificial intelligence, neural networks, are inherently bad at Occam's razor. They will greedily consume everything they can from the data set to try to squeeze the last bit of predictability out of the data set. So in the space example, a neural network could be and has been applied to try to predict whether or not a certain mouse will react in a certain way when exposed to space. But these models take the entire genetic makeup of the mouse into consideration. So you end up with a model that takes the mouse's genome as input and how likely it is to be affected by the space environment as output. And that is bad in various ways. First off, super inconvenient because you really want to sequence the full genome to make this relatively simple prediction of whether or not you will react badly to the space environment. That's a practical limitation that makes it hard to use as any kind of tool in practice. But it also takes away any possibility of understanding the underlying process. You just say 3 billion base pairs in and one prediction out. Right. What's going on? And that's what you get with a neural network. With symbolic artificial intelligence, we identified a 2-gene model, not linear, but a 2-gene simple model that was able to accurately predict whether or not these mice would experience the adverse effects on their skin. And you have a model that's easy to apply in practice. You can actually use this in a diagnostic or prognostic setting. But secondly, it also gives the opportunity to think about what happens. Why are these genes actually impacting the mice in that way? And you can relate it to other previously known information about the same genes in a different setting. So one of the big problems when doing symbolic artificial intelligence is that you're actually searching through an infinite space of possible explanations. So if you're trying to figure out if something is related to some other thing in one way or another, then if you just start writing down the ways those relations could be, you'll never finish. So that's essentially an infinite list. And that's why you can't really exhaustively say that you've searched through all possible scientific theories. And that's good news for scientists, because that means that they'll never run out of things to do. They have to be the intuition or the brain that comes up with the interesting things to try. And here I think that the human brain is leveraging two core principles. One is the intuition that allows the brain to guess in some weird way based on prior, not entirely related knowledge, what is worth exploring. But at the same time, we also have this other property that we are a massively parallel thinking unit. We think a lot of thoughts at the same time. We don't know we're doing that, but we do. So when we get an idea in the middle of the night or something like that, it's actually because we've been thinking maybe millions of things, and then the good thing popped into our mind. So in order to mimic that, in order to actually find good explanations in this infinite set of all possible explanations, we also have to combine a good intuition about what to try with the ability to explore a essentially infinite space of explanations. The intuition part in our system comes from the subsymbolic methods, transformer models, and other approaches that are related. But the most interesting thing I'd say about our technology is the way we deal with the massive search around the things that we actually do want to try. So once the intuition part has decided what to try, then in order to test let's say maybe billions of different solutions that still fit the bill, we have modeled all of that as a quantum field. So we actually take the entire problem of input and output and translate it into something that is akin to the way you would formulate a quantum field in the Feynman formulation. It's a way where you express all possible paths a particle can take through space, and then you add all those up together. You integrate them, as we say. That's why it's called the Feynman path integral. And that's actually a very similar problem. You have particles traveling through space along an infinite set of trajectories at the same time. We have possible explanations from A to B that can be composed in such a way that there's also an infinite set of paths. And we tackle those two problems in a way that's very similar. So we translate the entire domain into a mathematical abstraction that we call a Q-lattice. And the Q-lattice is this idea of trying to map a space between the things we have as predictors and the thing we want to predict. And then we use the same principles as you do in quantum field theory, a principle or a method actually called quantum lattice gauge simulations to divide and conquer that space. That allows us to effectively search with very high probability the important parts of that space. And it also allows us to use a lot of tools and tricks that have been learned by quantum physicists when they've built supercomputers to tackle that problem. So we can both leverage the core idea, but also some of the tricks that has allowed that to happen. So the end result is that the intuitive part of our algorithm can suggest interesting ideas that maybe limits us down to, say, a few million or billion options, and then we can explore that space very efficiently with the quantum or the Q-lattice algorithm. And that's why we find the needle in that haystack, this difficult to find formula in the haystack. And I think that the combination of those two, the hybrid combination of those two, the subsymbolic intuition and the ability to execute this massively parallel number of analyses at the same time and actually have them learn from each other. That's part of what the Q-lattice algorithm leverages, is why we can do this.
We'll be back right after this.
Hackers and cybercriminals have always held this kind of special fascination.
Obviously, I can't tell you too much about what I do.
It's a game. Who's the best hacker? And I was like, well, this is child's play.
I'm Dina Temple-Raston, and on the Click Here podcast, you'll meet them and the people trying to stop them.
We're not afraid of the attack. We're afraid of the creativity and the intelligence of the human being behind it.
Click Here, stories about the people making and breaking our digital world.
AI machines. Satellite. Engine ignition.
Click Here.
And liftoff.
Every Tuesday, wherever you get your podcasts.
Since the Industrial Revolution, the development of our economy has been centered around the idea of products that you buy and install and run. And we've been through an era, the cloud era, where that has not been the norm. We've had a push in the different direction where we've moved more and more services into the cloud. And I think that people have come to assume that that is just the new normal. I think that it's going to be a relatively short interim period when we look back at this from, let's say, 50 years from now. We'll see. They ran everything in the cloud from 2008 until 2025, let's say that. And then we went back to the norm that you buy products and then you use them where you are. This decentralized idea of a market and our industry and the structure of our industry is going to revert to that. And I think that what drove the cloud economy was the dependency on information. The fact that information, the more you could collect and centralize, the more powerful your technology was. That's what drove Amazon and Google and those kind of companies to where they are today. But if you think about that, that has actually already come to an end. Most of the time, when I need to consult or find information of some kind, I prefer to use my own AI, and that's a super local device. It's running on hardware that I control, and it's actually as good at the information part as the centralized systems are. And at the same time, it has all the benefits that we've forgotten: the robustness, the privacy, trustworthiness. And when I say the robustness, that might be actually the most important one. If my AI breaks down today, the neighbor's AI will not be impacted at all. So there's a lot of disadvantages to centralization that we've just learned to live with because of the importance of centralized information. I think that AI will go through a miniaturization phase where the hardware required to run artificial intelligence is getting smaller and smaller, and it won't be long until it runs on everything, even your coffee machine. And at that point in time, what's actually the point of a cloud economy? Why would you actually leverage your AI services to a cloud provider if there's no functional difference and you're giving away your autonomy, your privacy, and also taking a risk on the robustness side? Of course, the big cloud providers will not be the first movers here. Like their business is centralized about offering this. There could also be a slight tendency on them to be the bootleggers in this situation, where they actually also have an interest in, through regulation, making sure that it's better to run it in the cloud, because you have to have it approved. Because that's one thing that could really stop this decentralization. If small companies can build and operate and sell, deploy their own AIs, then the push for decentralization and the end of the cloud era will come from there.
Not just small companies, but smaller countries too. I was in Africa 2 weeks ago, and your take is quite popular.
Yes, I can imagine, because there's also a taking back control element here, which is quite central, I think. So when I think about it, I'm thinking mainly about individuals and companies taking back control. We've gotten used to that somebody can read what we do when we browse the net, but really, is that good? Why have we just accepted that? Imagine that I took a Renaissance thinker out and said, you cannot write anything anymore without sharing it with a big company in the US. That's how it is. So Voltaire, if you want to write it here, Google knows what you're writing. I'm not really afraid of Google abusing these things. Maybe I should be, but I'm not really. But I do have a very strong desire to actually control the environment that I operate in, to actually have full control of my privacy and my functionality. And AI will give us that. The functionality we're actually after can move all the way to the edge now. And yes, for people in, let's say, in Africa, that's going to make a huge difference. I was born in 71, got my first computer in 81, and that was a pretty big change in the world. Suddenly you had a world where we had typewriters and TVs, and now they could be plugged together and you could use your typewriter to write things that happened on the screen. But not only that, you could also program it to do things. And within, let's say, 10 to 15 years, that had really changed so many things. I think we sometimes forgot how much was actually changed in that phase. But if you think back to a manual, not even electronic typewriter, that's the kind of world we lived in. Then the next big revolution was in 92 with the internet. I was actually just starting my studies in here, and I ran across the internet in 91. The smartphone is another example. And in each of these phases, there's been a significant impact on the way we work. We've been able to become more connected, more efficient in some situations, more centralized, also more decentralized. It has changed a lot of things. And a lot of jobs have been made obsolete or have been changed to such a degree that people who used to do them did not really feel up to taking them on anymore. So there's been a lot of interesting changes to our labor market. And sometimes the AI revolution here is being compared to that. And yes, there are some similarities. But I think it's important to be aware of that this is also very different from those other changes. Because in all of those changes, what we've seen is technology making the way we work much more efficient. And right now, when people think about AI, they also tend to think about it as a tool that makes them more efficient. Think of ChatGPT or various types of generative AI. They just do things faster. The human is still the person doing it. It's just a tool in their hand. The prospect of AI, and actually what's closer than I think most people realize, is AIs that are more autonomous agents in a different sense, where artificial intelligence gets a high-level objective, and then it runs with that for a long period of time. So it could be like a marketing objective or a data analysis objective, or things that you would normally have a human do with powerful tools. But here the tool becomes equivalent to the human. And if you take this to the extreme, you can actually imagine, I sometimes use an example where you imagine a company run only by AIs. Like you could imagine that in principle, that every single employee in the company was actually an artificial intelligence working together. So maybe there's one boss somewhere in the top reaping all the benefits, but that's a feasible scenario in at least in some industries. And in that sense, it's a different type of automation. We're automating whole workflows or whole job functions that would require humans before. So, and not only are we automating job functions, we're automating highly skilled job functions. Some of the most highly trained people in our society are working on some of these things. So the impact on society is going to be bigger. First of all, because knowledge work being automated impacts some of the most influential people in our society. There's also going to be more resistance than when we automated the job of the elevator operators. But it also means that in the past, people have moved up to more meaningful jobs in many situations. You've moved from manual labor towards more and more knowledge work, and other people have moved toward the service sector. Now it's the knowledge workers themselves that are being automated. Where can they move? They can actually only move back to the service sector. That's the only remaining place where I can see large amounts of people go for work. I'm an optimist in general, so I think things will be all right, but it's not going to be like the other waves of automation. It just isn't. Yeah, I don't think people have grasped it. There's still a tendency to think about AI as a tool and not as a real intelligent being capable of replacing a full human and their entire job.
This show is produced by me and Anthony Green with help from Emma Silikans. It's mixed by Garrett Lang with original music from him and Jacob Gorski. Thanks for listening. I'm Jennifer Strong.